Good morning, sir. Today, I, Yash Sharma of roll number 2K20-ME-311, Yashwant Raj of roll number 2K20-ME-313, Yerish Raj of roll number 2K20-ME-314, and Yuvraj of roll number 2K20-ME-317 are going to present our group activity which was given to us in best possible way as we can. Uh, Yashwant, can you? Okay, so here, this is the latest innovations in pumps that we have gone through by studying the research papers. Here, firstly, the latest innovation that we get is hydraulic metering that includes series 500 hydraulic metering pumps from Neptune Chemical Pump Codot are adjustable while running through 100% of range. They have capabilities to 80 GPH simplex and 160 GPH duplex with pressure up to 3000 psi. The 1/3 HP single phase motor includes a built-in automatic thermal overload. Then the second one is reversible grinder. The 2 HP model Shark grinder pump from Zoiler engineered product has a reversible stainless steel star cutler and plate hardened to Rockwell C5560. The bidirectional design eliminates cutter jams. The pump's discharge configuration is 1.25-inch NPT vertical. The standard or explosion proof three-phase motor runs at 3450 rpm. Its coolant technology effectively disperses heat, promoting long service life.
So this is Yashwant, roll number ME313. The next two innovation technologies in pumps include submersible mixers and air-operated pumps. So moving ahead with submersible mixers, Anamix horizontal submersible mixers from KSB homogenize and thicken wastewater and sludge. Units have an 8 to 24-inch self-cleaning propeller with up to 13.4 horsepower and 1750 rpm motor. A tandem mechanical sealing arrangement seals the shaft, while a leak-proof cable entry prevents water from leaking inside the motor. The pumps have a close-coupled design, gear drive, and cable plug that plugs and unplugs without an electrician. Air-operated pumps. Pumps in America, air-operated double diaphragm pumps include the stall-free air motor runs without lubrication and uses half the industry standard for air consumption. Explosion-proof conductive plastic construction resists deterioration even in low pH locations and is lightweight. The 2-inch model weighs 41 pounds, and the maintenance-free high-suction lift comes from double-hinged diaphragms, long stroke, and self-cleaning slurry valves.
Now, I, Yerish Raj, roll number 314, is going to present this. The next 2 points are high volume pumping and microprocessor management. High volume pumping, electric or diesel driven self priming pumps from Griffin Pump and equipment inclusive have non clogged impellers that handle stringy materials and solids up to 4.5 inches. An ample clean out port enables operators to clear debris beyond 4.5 inches without removing the suction pipe or hose. The pump's lever flows to 17,000 GPM and head capacities of 240 feet or more. They are available in vacuum assist, diaphragm prime, or compressor. Microprocessor management. The Chemtech XPV series pump from Placer inclusive a unit of IDEX Corporative, combines variable speed parasitic pump technology with control electronics. Duplex models have two pump heads that deliver twice the flow of two different chemicals simultaneously. The microprocessor handles various input signals types and onboard timers programs to customize the pump to any application.
Now I'm Yuvraj, roll number 317. I will explain the other 2 points. High flow model pump and heavy duty hose pump. High flow model pump series HF horizontal pump for Serifluic Limited has a flow of 400 GPM or 170 feet total dynamic head. Come in high temperature poly propylene or chlorinated polyvinyl chloride construction and are ANSI dimension with the optional ANSI 150 pounds plank connection and enclosed impeller molded to close tolerance allow the pump to operate at a peak horsepower. Efficiency for many flows and head requirements, including dry roll capability, all have an external Type 21 mechanical seal with silicon carbide seal faces. Models with double mechanical seals require water lubrication for solution containing. Now, heavy-duty hose pump with operating pressure of 232 psi and flow rate of 350 GPM. Heavy-duty SPX pump from Walton Marlow Bradley pumps handle abrasive slush with no effect on the pump life. Peristaltic hose pump work by alternately compressing and relaxing a machined hose pump element between the pump housing and compressing shoes. The fluid ahead of the shoe is pushed towards the discharge, while the rebounding hose behind the shoe draws in more fluid, with 100% compression at all times. The pump do not slip, providing metering accuracy and pressure performance. With no pump seal, seats or valves, abrasive slurries are no problem. With a self-loading design, hose replacement is quick and easy.
Now we are going to discuss one of the research paper that we have gone through. We have seen some research paper for the understanding of the new technology of pumps, and after that, now we will discussing an research paper that we found bit interesting. So this is the research paper that is on determining hydraulic ram pump feasibility. It is basically for the audience which is situated in rural areas, as rural communities looking to construct small to mid-sized water systems for manufacturers and installers of hydraulic ram pumps. So the background of this research paper includes hydraulic ram pumps that have been used for over 200 years to pump elevated water without an external energy source. They can be constructed from common pipe fittings that are available in rural areas of developing countries. As a result, ram pumps are more affordable and easier to maintain than their alternatives. However, the feasibility and performance of hydraulic rams are difficult to predict. Currently, they are designed by experimental rules of thumb or incomplete sets of non-dimensional equations. Both methods leaves the designer to guess critical parameters which can result in a failed design. This unnecessary causes feasible projects to be abandoned and projects destined for failure to be constructed. Now, here we have discussed the purpose of research paper, and afterwards we have discussed the purpose, and then where we have also in research paper there are methods for performing the same. Then there are some results, then implications for targeted audience, as the results provides a table that allows user to determine the minimum requirements of a site arrangement. This will increase the sustainability and affordability of water system developing areas. So these are the implication for target audience. This is the abstract of a research paper where hydraulic ram pumps have been used for over 200 years. There's water for only for 200 years to pump water using only the potential energy of elevated water. And today, the low price and simplicity of the materials and methods required to construct ram pumps makes them an excellent option for a small and mid-sized water systems in developing countries. Uh, so these findings encourage a wider proliferation of hydraulic ram pumps through more accurate designs tools and can reduce cost of water system for small developing communities. Afterwards, uh, in the research paper, there we have seen its introduction and ramp pump setup cycle, where ramp pump setup cycle, where figure is shown here that it is the ramp pump setup, typical ramp pump setup cycle. Now this is the research paper that we have gone through, one of the research paper that we find bit interesting. A few terminologies are being discussed. Now afterwards, Yashwant will give brief overview of the research paper.
So now I, Yashwant Raj, will discuss the current design methods discussed in the research paper. So currently most RAM pump systems are designed by assuming a certain input flow rate and an efficiency of 60%. These two parameters can be used along with lift height and fall height to calculate delivery flow rate using definition of pump. Arbitrarily assuming an efficiency of 60% is problematic because real efficiencies can range from 0% to 65% and with 11 independent variables. So this design method leaves users to guess input flow rate and fall height their pump will require across wide experimental ranges. However, these methods do not consider cases where maximum velocity or input flow rate of the water is insufficient for certain lift heights. As a result, they cannot be used to reliably determine the feasibility of a design. Therefore, now we will discuss a methodology. A model was developed to predict the fall height, fall to length ratio, and drive pipe flow rate required to achieve a certain spike pressure. This model can be applied to any ram pump design with a single waste valve. The design basically features a drive pipe with an inner diameter of 34.5 mm and a wall thickness of 7.6 mm. Experiments were conducted using both a brass swing check and weighted poppet style brass spring check valves. The same nominal size as the drive pump was used for the internal valve and waste valves is shown in figure 2. The increased lift heights were simulated by partially closing a globe valve on the end of the delivery line. The maximum lift height corresponding to an efficiency of 0 was measured by closing the global valve completely. The ram pump was tested under 5 different cases with unique combinations of fall height, waste valve weight, and drive pipe length. For each case where the water velocity was sufficient to close the waste valve, the ram pump was tested at multiple simulated lift heights. The input and output flow rate were measured for each lift height by recording the time required to fill a container of known volume. Here we have discussed the different experimental values. There are basically 5 experimental test cases. For the fifth case, the maximum water velocity at the waste valve was not enough to close the waste valve regardless of input flow rate. As a result, no water could be delivered, regardless of simulated lift height. The graph shows experimental ram pump efficiencies, and the range of efficiencies is reported between 0 to 57%. The results indicate that efficiency is dependent on several variables. The operation of a generalized ram pump was modeled to provide a conservative estimate of maximum lift height. So now moving on to evaluation, we have estimated the research paper has basically estimated the spike pressure. To ensure drive pipe has enough length to fully develop the pressure spike, the drive pipe length should be sized between 150 and 1000 times the diameter of the pipe. And to determine how accurate the application of this equation was to experimental ram pumps, 3 tests were conducted to measure the pressure spike. An equation with describing the water velocity needed to overcome the mass of the valve wafer was needed to complete this analysis. Since the waste valve closure must be rapid for the pump to function properly, the valve was modeled to close immediately once the gravitational force of its wafer mass was exceeded. And then the force analysis was done, and through that the research paper basically discusses the calculated and measured spike pressures. From the experiments, it appears the spike pressure is between 85 to 90% of theoretical spike pressure. So based on this observation, the model uses equation 2 and multiplies the product by zero point 0.8 to calculate spike pressure. Accurately predicting the spike velocity is important to predict the amount of inflow the pump requires. So from now on, Yerish will discuss the acceleration of dry pipe flow.
Now, acceleration of dry pipe flow. The acceleration of flow in the dry pipe must be modeled to predict the amount of water required to complete a pump cycle, the pump's frequency, and the maximum spike velocity attainable. These quantities are used to calculate the lift heights of a pump can achieve and the corresponding supply flow rates required. Each time a ram pump cycles, the water in the dry pipe begins at negative velocity from the recoil of the previous cycle. The fluid inside the dry pipe is analyzed as a control volume, and the acceleration of the flow is modeled as one-dimensional incompressible flow. These assumptions eliminate relative motion in the fluid, allowing for analysis based on rigid body translation. When analyzed as a rigid body, the control volume acceleration can be described as Newton's second law, as shown in equation 5. We can see the equations where the m is the mass of accelerated and f is the acceleration of force. F is the force associated with pipe friction. Fm is the force associated with the minor losses, including the waste. The shear stress on the pipe well can be modeled with the same method used to predict pressure drop in pressurized systems. Pressure drop per unit length is related to the wall shear stress by equation 8, and the Darcy-Weisbach equation was used to model pressure drop, which is given in equation 9. We can see similarly some of the equations such as for the most ramp pump application, the dry pipe flow becomes turbulent soon after acceleration begins. For turbulent flow, FD can be approximated by equation 11. Now rewriting the equation 7 using equation 9 and 11 yields an expression for pipe friction force when the flow is turbulent in terms of physical constants and velocity. The expression is given as shown. Now the result for the turbulent case as shown in equation 6:16 indicate the flow will stop accelerating, that is dv by dt is equal to 0 at a velocity determined by the fall to length ratio and the characteristics of the dry pipe and the total loss coefficient of the system. This implies that for a system where the effective weight of the waste valve can be adjusted, the fall to length ratio limits the spike velocity even for designs with large fall heights. The insight is largely absent in the literature. Now, direct application for acceleration model. The solution can be used to estimate how much time Ts is it takes the water to reach a certain spike velocity Vs. This time can be used to calculate the maximum number of times a pump can cycle in each minute. The maximum frequency can be found from the equation F is equal to 1 by Ts plus 2L by Cw. Frequencies measured during testing were compared to maximum frequency predicted by the model. The comparison is shown in figure 5, where the frequency is displayed in cycles per minute. The experimental and model maximum frequency is showed as in the graph. Setting neta equal to unity provides the maximum possible deliverable flow rate, which can be added to the maximum possible waste flow rate to determine the maximum input flow rate required. The model was run over the same conditions as the experiments. The amount of wastewater required for the experiments was compared to the maximum amount of wastewater the model predicted. This comparison is displayed in the graph 6. Now estimating minimum fall height required. The maximum spike velocity of a ram pump can also be limited by the available fall height. To determine the amount of fall height required for a certain spike velocity, conservation of energy was applied to the flow in the dry pipe using Bernoulli's equation. This is expressed in equation 19 where V is a function of time which can be calculated along with the excess from the integrating equation 14. The integral of equation 19 is calculated according to the trapezoidal rule where an average value of P loss during a time interval is determined from the numerical solution for Vt. The model is implemented in MATLAB script in the appendix. The script can be used to estimate the maximum spike pressure a pump can achieve as a function of dry pipe length, diameter, material wall thickness, average angle, bends, fall height, and the available supply of flow rate. Delivery flow observations. When the results of this model were compared to the experimental data, the model was found to be inaccurate as the ratio of lift height to the fall height increased. The percent error of the experimental data is plotted in figure 7 with the lift to fall height ratio in the x-axis. The figure indicates this model significantly underpredicts delivery flow as the lift height to the fall height ratio increases. As we can see in the next graph, since existing correlations could not predict the delivery flow of the design reliably, the model developed in this paper does not predict the delivery flow of the potential designs. Further, Yuvraj will continue.
I will explain the producing reference table from model. The acceleration model was conservatively applied to the several example scenarios to determine the minimum site characteristics required to pump water from the ramp with waste valve weight that can be adjusted. The ratio that we obtained was similar to 1.6 ratio recommended by the Young's when it is divided by 0.8 factor used to determine the difference between the theoretical and experimental pressure spikes. This solution also assumes the drive pipe containing no tight band, a spring check valve is used for the waste valve. In figure 9 and 10, the list the minimum site characteristics required to deliver water to different range of lift height using matrix and English unit respectively. To evaluate a site, one should start by finding the applicable lift height range. The, then compare the site attribute with the minimum fall to the length ratio of HF by L, where HF is the fall height and uh, QS is known as the flow supply rate required to the type of dry pipe being considered for the design. These tables shows the minimum side characteristics required for the various ramp configuration in the matrix unit, and in figure 10 is also the same. Now moving on to the next page, as any pump approaches the minimum requirement for its lift height, the efficiency, and therefore the flow rate, it will deliver decrease exponential as shown in figure 8. Site that requires low value for the characteristics such as steel pipes for low delivery heights will deliver a small fractions of their inflow. The arrangement of the site should seek to exceed the minimum requirement to deliver more water. For a design with adjustable waste wall to operate correctly, its walls water must have the correct amount of weight to prevent the valve from closing until the flow reaches the desired spike velocity. However, adding additional masses will raise the amount of supply flow required as and many raise the fall height and average dry pipe angle required. The weight required for the maximum spike velocity can also be estimated with the MATLAB script or with the equation 4. In figure 11 and 12, the listed aggregated mass of the water and the additional weight is required in grams and ounce respectively for the same scenario listed in figure 9 and 10. Now the math, coming to the conclusion, the characteristics of the drive pipe acceleration and the pressure spikes allows user to predict the maximum lift height of the most ramp pumps designed more accurately than previous design methods. While ramp pump will deliver water to the lift height below their maximum compression, with experimental data indicated current model for predicting delivery flow are inaccurate in some cases. Users can also make more informed projects designed by using the provided reference scenarios or the evaluating specific design in the numerical modes. The modes can be used by those designing or turbo shooting ramps pump system to better understand how different variable effective pumps perform. While the experiment data supported the finding of the model, the data was only recorded over a limited range of design scenarios. Additionally, more research is needed to accurately predict the amount of water pump can deliver each cycle. A dimensional analysis that includes the fall of the length ratio as a parameter is a good candidate. The references that we are taken for this research paper by the author was drive pump of a hydraulic ram and frictional losses table and other universities books and research papers. Thank you.